Hello everybody, and welcome to our class video about the impact of a scale factor on the perimeter, area, surface area, and volume of 2D and 3D figures. Our learning goal is that you'll be able to determine the new perimeter, area, surface area, or volume when a scale factor, that is, we're multiplying, is applied to a two-dimensional or three-dimensional figure. Okay, so let's get started. We've been doing some investigations in class prior to this video, or you might be watching the video before those days if you're really ahead of the game. But this video is intended to tie together the things that we've been learning by discovery in class. Okay, so let's first look at when all of the dimensions, that is, dimensions such as length, the width, the height, the radius, things like that, when those are changed by the same scale factor. Remember, the scale factor is what the dimensions are being multiplied by. Okay? When we have a 2D figure, then when the perimeter would be multiplied by the same scale factor that the dimensions are. So if the length and the width are all multiplied by 2, then the perimeter would be multiplied by 2. For a 2D figure, when we apply a scale factor to all of the dimensions, the area is multiplied by the scale factor squared. When we have a 3D figure, then when we apply the same scale factor to all of the dimensions, I'm emphasizing that for a purpose because it has to be applied to all of the dimensions, then the surface area is multiplied by the scale factor squared, just like the area of a 2D figure. The volume is going to be multiplied by the scale factor cubed to the third power. If you think about it, these are related to the type of units that are usually associated with these variables. The perimeter, let's say we're using inches, would be inches. The area of the same figure would be in inches squared, the same power as we apply to the scale factor. Likewise, the surface area would be measured in inches squared, so that's the same power on the scale factor, and the volume is inches cubed, hence we're cubing the scale factor. Okay, so let's look at an example. So we got a store owner who's going to build a parking lot, but he changed his mind at the last minute to double the length and the width of the parking lot. So notice we're changing all of the dimensions, both of them, for the parking lot. Okay, and we're using the same scale factor. Okay, the original parking lot was going to require 260 yards of curbing. So the curb runs around the edge, so that would be talking about the perimeter. And it required 4,000 square yards of concrete. Concrete covers the entire area, so that must be talking about the area of the parking lot. Okay. We want to know how much curbing and concrete will the new parking lot require. So in other words, we want to find the new P and the new A. Okay, we can handle this. So here's a picture of our parking lot. Yay, it's a rectangle. So the perimeter is 260 and the area is 4,000. We are going to double the length, so the length is being multiplied by 2, and the width is getting multiplied by 2. So our new parking lot would look something like that. Okay, if we look at the rules up above, the perimeter is going to be multiplied by the same scale factor. Okay, so since our scale factor was 2, because we're doubling, the perimeter is also going to be multiplied by 2. So our original perimeter, 260 times 2, would mean a new perimeter of 520 yards. There, that was a pretty simple calculation. What about the area? Okay, so if we look at the rule, the area is multiplied by the scale factor squared. So since our scale factor is 2, we need to multiply the area by 2 squared. What is 2 squared? Well, 2 times itself is 4, so the area would be multiplied by 4. You can visualize this if I divide our new parking lot into different sections. And you can see that the original parking lot of 4,000 could fit 4 times inside the new parking lot. So the area is 4 times bigger. Okay, so if the area is 4 times bigger, 4,000 times 4 would be 16,000 square yards. Okay, not too bad. So let's look at now when only some of the dimensions are changed by a scale factor, not all. Or say they all are changed, but the scale factors are different. Okay, for a 2D figure, the area is going to be multiplied by each scale factor applied to both of its dimensions. So we got 2D, it's 2 dimensions. So let's just say for a rectangle, we have the length times 2 and the width times 3. Okay, so those are my 2 dimensions. We got to multiply the area by both scale factors. So if I multiplied it by 2 and then by 3, I would have area times 6. All right, so let's look at a volume example. Well, volume is 3D, it's 3 dimensions. We're still going to multiply it by all of the different scale factors, but there will be 3 of them this time. So let's say we do length times 2, width times 3, and height times 4. We have to multiply the volume by all of those, all 3 of them. So if I multiply 2 times 3 times 4, the volume is actually going to get 24 times bigger. That's a lot of volume. Okay, so now what about perimeter and surface area? For perimeter and surface area, it depends on the dimensions. There is no magic rule. So if only some of the dimensions are changing, or if the scale factors for the different dimensions are different, we can't make a conclusion about the perimeter and surface area. We need to know the actual measurements. Okay, so let's look at an example. We're going to look at some soda bottles. So we got a 2-liter soda bottle, has a radius of about 1.3 times larger than a 1-liter bottle. And it's got a height that is about 1.16 times larger. Okay, so we want to know how many times more volume the larger bottle holds. Some of you have caught on and are thinking in your head, well, duh, the volume is multiplied by 2. 1 liter changed into 2 liters. 2 times more. Okay, so we really have the answer to our question there, but let's check if the dimensions, the change in the radius and the change in the height, actually go along with the 2 times change in volume. Okay, so we can approximate these soda bottles as a cylinder. They are not perfect cylinders, but it's the closest shape we got, and I think it'll do fairly well. We know that our radius is going to be multiplied by 1.3, and our height is going to get larger by 1.16. Okay, so if we apply the same thing that we did up above with that first volume example, we've got radius times 1.3 and height times 1.16. So then what would the volume be multiplied by? But wait. Volume is 3 dimensions. So I have to have all 3 dimensions represented before I can determine what the volume is multiplied by. Where's the 3rd dimension? Well, the key is in the radius. Okay, so the radius for a circle doesn't just extend in one direction. If I change the radius of a circle, I'm also actually stretching the circle in a different direction. Okay, so the radius is actually counting twice because the radius of a circle goes in 2 directions. It goes horizontally and vertically and diagonally and all those other ways, but you know what I mean. So the radius is going to change the volume twice. So to find what the volume is multiplied by, now that I have all three dimensions, I need to multiply all three scale factors. 1.3 times 1.3 times 1.16. If I do that, I'll get the volume times 1.9604. Well, that's pretty close to our volume times 2. The difference is probably in the fact that we approximated this as a cylinder when really those soda bottles are not cylinders. But hey, we got pretty close. Alright, so we'll do some more examples like this in class. Feel free to ask questions, and I'll see you later. Bye.